So we're going to start looking a little more in depth in axial load. And one of the first things that we'll talk about in axial load is what's actually happening when we load something axially. So for example, if we have some bar, what happens when we actually put load, attached to the ground I guess, put load on that bar, right? We load this thing up with some load P. When we do that, there's actually some distortion around that load, right? So where that load is happening, there's like this little bit of distortion occurring where this load is attached, right? It's not quite a perfect example of our average stress equation. Like if I were to say take a section through here, call that AA, and I look at just this one little section of the beam, I'm going to get this kind of variable stress. This variable stress that's occurring because of the load. It's not going to be perfect because it's deforming a little bit more around the load than it is somewhere farther away from the load. Like if I took an average cross section here, where I'm a lot farther away from the load, this is where I could see that my stress is actually acting like a stress. Like my load is more uniform. I get that average stress equation where the normal force over the area, whereas here the normal force, it's, you know, maybe a little smaller on the sides, a little larger in the center, it dips down a little bit. It's not a perfect average. There is some deformation that occurs around that load. And this concept of this deformation being not noticeable farther away is something called Venant's principle. And really all this is telling us is that, you know, hey, don't take a cross section really close to your load. You want to be at least one cross-sectional distance away, one width away from where that load is being applied. So I didn't finish this word, principle. Same Venant's principle says that when you have these two loads, as long as you're a sufficient distance away, then your equations become valid again. So the common equations, stress and strain. And they typically say that this distance should be at least equal to the largest dimension of the cross section. So either your width or your thickness. Typically your width, so however far back this thing goes, you want that to be the same amount down from the load. Largest dimension of cross section. So it's just a good rule of thumb to know that there is some localized distortion at your ends here. Even at this other end where the reaction is occurring, you're going to have this localized distortion where it's kind of pulling out as well. So there's deformation going on around this reaction as well where it has load there. So these are just important for us to note because as we go on to this axial load stuff, we're going to be wanting to look at the inside for these axial loads, right? Just as we had been cutting through members with shear and moment, normal, all of those we were cutting through. We are looking internally for the stress and the strain, right? You might have noticed if you did the Play-Doh lab experiment that I have up, that there was some deformation more so at the binder clip where you clip onto the Play-Doh. It was more likely to snap there because that's where the load was. So that's where more deformation was occurring than if you were to look farther down on your little strip of Play-Doh. So it's just something that we keep in mind. We know that it's there, but generally small enough that we can ignore it. It is generally causing such small localized deformations. They have a very, very small effect on what we're doing. So because of this, when we go to look at axial load, let's look at something that's loaded axially. Maybe it has kind of some irregular shape here, and it has this loading on it. Loading P, length of L, has this loading all throughout it. We're saying that when it deforms, instead of looking explicitly at the end here when it deforms, this delta, we want to take cross-section for each x. Take a dx, which I know you see a dx, you have an idea of where this is going. Probably going to be an integral. So if we have some object that's loaded like this and it's in the elastic region, then we can use our stress and strain and Hooke's law relationships to all work together, right? So our stress equation was the stress is the normal force over the area. Our strain equation is delta over the length, right? Change in length over the length. And then Hooke's law says modulus of elasticity is stress over strain. So we can take all of these puppies and combine them to get one magic axial load formula, right? I can put my stress and my strain in here. So I have normal over area times length over delta. And what I get, if I treat it as an integral, where my normal force maybe is changing with x, maybe my area changes with x, my delta changes with x, my I don't want to write it like that. My delta, let's write it d delta dx instead. It's a little confusing with the d's and the deltas. So my change in delta over the change in length there. What I can get is I can get an integral when I sub all of these in together. So I can get my modulus of elasticity is that normal force as a function of x dx over area as a function of x times the d delta, change in delta. And what I can do with this is solve for delta, right? Because I don't want to use this end delta because of the deformations. So instead I'm going to use delta to take an integral, right? Because instead of having d delta, I want to integrate that. Integrate in x dx over a of x times modulus of elasticity. And I want to integrate it over this whole length that I have so that I can find my full delta is 0 to the full length of whatever my normal force is through that axial load there times dx over the area as it changes with x. Whoops, that's backwards. Times modulus of elasticity. So this equation is really useful for when things are changing. If things aren't changing, right, we have a constant modulus of elasticity, constant area, constant loading, then we can shortcut it with what we derived up here, which is delta is the normal force times the length over the area times the modulus of elasticity. So this one is only valid, 1, in the elastic region, 2, if everything is constant load, constant area, that's when this is valid. But this is a super important equation for us. It lets us do even more things with our stress and strain calculations, relating them to the modulus of elasticity using this relationship. The integral one is really, really helpful too, especially if you have changing loads and changing areas that we couldn't really deal with very well before. Now we have this handy integral to deal with that, right? So we can find the displacement of anything that has an axial load. Anything that's being stretched or pulled is going to have some kind of deformation, some kind of movement, some kind of displacement. And that's what we're going to be finding first with these axial load problems, is whatever that displacement is. Now, we can also use these if we have multiple sections of something. So because we can do it in integral form, we can also do it as a summation. For example, if you have, maybe you have one section of copper and it's attached to a larger section of steel, and they have a different modulus of elasticity, they have a different area, you can do a summation with these as well, where your delta is just going to be the summation of each individual section, normal times length over area times modulus of elasticity. So just as you can do it with an integral, you can use the basic equation, or you can do it as a summation. And we'll take a look at a few examples to see how we can use this displacement. One last note on this displacement, though, is that anytime you're in tension, so this green example up here, we have the P, it's in tension, pulling either direction of our specimen there. Anything in tension is going to be positive. We're going to use that's a positive displacement. So tension gives you a positive displacement, but if our load were going the other way, going inwards towards the specimen, that would be compression, and for our sign convention, compression is going to be negative. So just keep that in mind. As we compress something, think about squishing in a little tube of Play-Doh. It gets smaller and smaller, so the distance, the displacements will be negative. Whereas if you pull on something, the displacement will get larger and larger, so you'll have a positive value there. So in this example, we have a uniform A36 steel bar with a diameter of 50 millimeters that's subjected to the loading shown. We need to determine the displacement of point D, as well as the displacement of B relative to C. So what we're going to do in this one, since we have multiple sections of loading, we're going to have to do a summation to account for all of the different loads, because we're going to have different normal forces in each of these different sections. Even though the bar is uniform, it has the same modulus of elasticity throughout, it has the same area throughout, it has different normal forces, as well as different lengths for each of these sections with these different normal forces. So what we're going to want to do is apply our equation, our axial load equation. Delta is the normal force times the length over area times modulus of elasticity for each individual sections, breaking this out into sections so we can find the normal force in each section and find the delta. Now, the delta is relative to the left-hand side. Anytime you're taking these displacements with this axial load equation, it's going to be taking the displacement from the far left point and then through your section. So for our first one, let's start with section AB, since it is our most left section. That's the one it makes sense to start with. If I go ahead and break out the section, I have my wall, I have my load, and I'm going to break through it, and I need to find what the normal force is. Well, I'll notice that the first thing I actually need to do is find what reaction is happening here at A. I've only got forces in the x direction. I have 80 kilonewtons, 40 kilonewtons, and then 70 kilonewtons to the left, which means that my reaction at A here is going to be 50 kilonewtons to the left, right? I need it to be in equilibrium, zero it out. So I have a reaction here of 50 kilonewtons a day, just from statics, right? So that tells me that my normal force here, my normal force through section AB, when I cut it, I'm cutting it, you know, right about here before I actually hit B, is going to be 50 kilonewtons. So now I have the end portion of this equation. This is the displacement of B relative to A. Right, this is how B is moving with respect to A, or with respect to our far side. So this is how B is moving. This section. I have N. I have L. The total length A to B is 2 meters. So I have L is 2 meters. The area of the bar is constant throughout, so I might as well just write that in a note up to myself. Area is going to be pi over 4 times 0.5. Oh, sorry, 0.0. No, oh my goodness. 0.05 meters squared is going to be my area for all of these, since the bar is constant. It has a constant area throughout. So there's my area. And then I need my modulus of elasticity for my bar E, which is not given here, but it does give me the material. Right, it tells me an A36 steel bar. I want to go ahead and flip to my table in my textbook just to see if it's in there, right? If it's a known material that has a known modulus of elasticity. So I pull up my table, here's my modulus of elasticity, materials, A36 steel, perfect. It gives me a modulus of elasticity of 200 gigapascals. 200 gigapascals, which again is going to be constant for that whole bar there. It's all made of A36 steel. So 200 gigapascals, which a giga, if you haven't seen it in a while, is 10 to the 9th pascals. So that's it. Those are all the ingredients I need for my equation, so I can pop them all in there now. And my 50 kilonewtons, which I'm going to go ahead and convert to newtons. So 500,000 newtons times the length of 2 meters over my area that we found up there. I hadn't typed it into my calculator yet, but that probably would have been a good idea. And then 200 times 10 to the 9th pascals, putting everything in base units so I don't mess up any of my unit conversions later, right? I don't want to have kilonewtons and gigapascals and millimeters. It's very messy. You want to make sure you're converting your units on these so that I can get a correct displacement of B with respect to A. When I punch it in my calculator, I get 0.000255 meters. So I'm going to have to repeat this for every section, because every section I take is going to give me the displacement with respect to the section next to it. So this displacement, this next section, my section of BC, if I look at my section here, cut through, I have the 50 kilonewtons, the 80 kilonewtons that are actually acting at point B, and then I cut before point C. So my normal force going through here is going to be in the other direction. Undo. It's pointing to the left. My normal force is 30 kilonewtons to the left. Right, so what does that mean? It means that my section BC is in compression. right? Here, my section BC, normal was pointing out. That's positive convention for my normal force. So my displacement was positive. That whole section was in tension. Now my section BC here is actually in compression. Right? Just the section BC here is in compression. So for a normal force of negative 30 is really what we would call it, a negative 30 kilonewtons. My length is going to be the length of just section BC here, which is 1 meter. And then everything else from before kind of just stays the same. The area is the same, the modulus of elasticity is the same. So my displacement, now this is displacement of C with respect to B, because we're looking at just the section BC length here, right? This section is the only one that experiences this negative 30 kilonewtons, the only one that experiences this 1 meter length, right? The only reason we included everything to the left of it is so we could calculate what the correct normal force was. So here I have negative 30,000 newtons times the length of 1 meter over all that stuff. A times E, same numbers as before. So when I punch that in my calculator, my displacement of C with respect to B is negative 0.0000764 meters. Again, that section is being compressed. So now even though B is moving outwards, point C is actually moving inwards, right? So they have these almost competing goals. The sections are moving in different directions, and we won't know till the end how the whole bar is moving together. So let's do our very last section. Section CD has the 50 kilonewton from the reaction, the 80 kilonewtons at B, the 40 kilonewtons at A, and then I'm going to have a reaction here, the normal force coming through here. So my normal force cutting through section CD, again, I drew it in the wrong direction. So it's combating that 40 and 80, and combining with the 50, I'm getting 70 kilonewtons for my normal force. Again, in compression, so this is a negative. Negative 70 kilonewtons is my normal force. And the length up here, so I have a negative 70, and then my length is this 1.5 just for section CD. Length is 1.5. So the displacement of D with respect to C, just section CD, how D moves in comparison to C, is going to be negative 70,000 newtons negative times 1.5 meters over the same area and modulus of elasticity that we've been using. I punch all that in my calculator, and I'm going to get that my displacement here of D with respect to C is negative 0.000267 meters. So now that we've calculated it for every section, all we're going to do is add the sections together. Once we add all those displacements together, just do that summation. That gives us the total displacement. It tells us how D is moving. Since A is fixed to the wall there, D is the point that has to move. So if I add all of these together, my 0.000255 plus, let me circle these. 0.000255 minus 0.0000764 minus and only minusing just because these are in compression, so they have minus signs on them, 0.000267. Punch those into my calculator, combine them, get my summation, so that the total displacement of point D with respect to A, or just total displacement of D, is going to be about 0.089 millimeters. I could leave it in meters, but I don't know, doesn't millimeters just look a little nicer? Makes it feel like maybe you're actually moving. It feels really, really small if you just leave it in meters. So that would be our total displacement of D. Now, it did also ask for what the displacement of B was relative to C, but we had to calculate that on our journey of calculating D, so we actually already have that. It's this guy right here. Displacement of C with respect to B. So easy enough. We solved both parts unintentionally. Had to go one part to get the other. So this is how we would do it if we needed to break it up into sections and do a summation. Next, we'll look at how we would do this if we needed to integrate. So in this example, we're looking at a post made of Douglas fir that we've stuck in the ground. It has a diameter of 100 millimeters and a triangular frictional load from that ground around it that is varying from 0 kilonewton per meter at the very top where it's not really touching the dirt, and then as you go farther down, the load increases triangularly to 10 kilonewtons per meter at the bottom here, 2 meters. They want us to determine this force F and the displacement of A with respect to B, which I realize I did not write on here, but our point A is at the top here, and then the point B is just at the bottom of the log. So two things we're finding, F and the displacement. So first things first is finding F, which is actually kind of going to be the easiest part of this because it's just going to be using our knowledge from statics, just applied in a little bit of a different way. Because we're not really used to seeing these triangular loads in a vertical sense. Because if I were to look at this log as a body, I would have this triangular distributed load, but it goes in this vertical direction, which is a little bit different than I'm used to seeing, right? But that's okay. We can still use our 1/2 base times height to find what the resultant is of that distributed load. So with my free body diagram here, there's my 20 kilonewtons. My distributed load at the bottom here is 10 kilonewtons per meter. And then I want to find the force F. So fairly straightforward, just a summation of my forces equals 0. I'm going to have the -20, the positive F, and then that distributed load, again, is just going to be that area of a triangle. So 1/2 base is 10 kilonewtons per meter, and then this height here is 2 meters. That's this total distance here is 2 meters. So a fairly straightforward equilibrium equation. I can solve for my F and find that it is 10 kilonewtons. And I got a positive answer, so that F is drawn in the correct direction as it was given to me in that problem statement. So first part done. We found what F we have to have for this thing to be in equilibrium. Now we just need to find the displacement, right? How much is this 20 kilonewtons kind of compressing this log here, this Douglas fir log that I have here? I've kind of assumed that it's going to be a compression, but I don't actually know, right? Because I have this variable load here, I'm going to need to come up with an equation to integrate along that load. So let's look at just a section of it. If I were to break off a little section of my log here, right, here's my log, It has the 20 kilonewtons, and then it has that triangular load that it starts before I chop through the log in order to find what my normal force is. Right, and this load here, there's my W as it goes down, and whatever this distance is, since it called it Y up here, I'm going to go ahead and call this Y as my distance down for wherever I'm chopping through. Right, this is kind of how we started our shear and moment diagrams back in statics, was cutting through and then having to create these equations. It's that same kind of idea, where now what I'm going to do is set up an equilibrium equation with my variables in it so that I can solve for n. And then I can go and use that axial load equation, that integration equation, to find the displacement. So for this triangular distributed load, I need to set up a ratio for myself to represent what W is. Because if I have the 2 meter depth that has this 10 kilonewton per meter height, then in my ratio triangle, for whatever the W is, my Y would be on the side here. So I need to solve this so that I can have a W term. So just using a ratio, I'm going to say, all right, my W over Y would be the same as 10 over 2. So this means that my load here as a function would be 5y. 5y. And now I'm going to go set up an equilibrium equation for this. So my sum of forces equals 0. And I still have that negative 20 is just constant, right? It's just a constant up top. Then I'm going to have minus, the way I've drawn it, the n is in the negative direction. So minus, right? It's in the negative y direction. Negative 20 minus n plus, again, it's that 1/2 base times height for that triangular distributed load. So it's going to be 1/2 times the base W is 5y, times the height, which is this distance along the side here, which we said is the variable y. So now if I come through and solve this equilibrium equation, I can have a function for my normal force there. And that function is 2.5 y squared minus 20. Just rearranging all the terms in there. So now that I have a function I can use, I can go ahead and use that axial load displacement equation. This displacement is the integral from 0 to L in, what was it, in dx over AE. So here my displacement from 0 to L, the total length is the 2 meter height of the log. So 0 to 2. My normal equation we just found, 2.5 y squared minus 20. Now in this case, instead of a dx, I'll have a dy since I'm working entirely in this vertical y direction. That's fine, my dx is taken care of, over my area. Thankfully, the area is constant. We don't have to come up with an equation for that. It told us it has a diameter of 100 millimeters, so I'm going to go ahead and put that in meters. 0.1, and then that's the diameter, so 0.1 squared times pi over 4. That's my area function. And then finally, modulus of elasticity, which wasn't given to me, but I was told that this is a Douglas fir. It gave me a material. So let me pop open my table, see if it's in here. Modulus of elasticity, material, wood. Here we go at the bottom here. Very bottom, wood, structural grade, Douglas fir. Modulus of elasticity is 13.1 gigapascals. 13.1 gigapascals. Awesome. So I've got that. 13.1 times 10 to the 9th pascals. And then I just go through and perform the integration to get my answer. So I'll spare you the gory details on the integration here. You can just pop it into a calculator. I took all this stuff in the bottom. I took that out first since everything on the bottom is a constant. And then I just did the top integral since it's the simplest. And I did have to convert my units here. So my units for my forces were all in kilonewtons. I went ahead and changed those all over to newtons so that my units would work out. So 2,500 y squared minus 20,000. And now everything should be in its base units. And when you pop that into a calculator, you get negative 0.33 millimeters. Which negative kind of makes sense, right? Negative sounds like something we would kind of expect, that this 20 kilonewtons would be enough to put this into compression so that A is being compressed towards B. It's getting shorter than it was before. Which, you know, for a 2-meter post, a third of a millimeter is a pretty good amount of compression, I would think. All of these numbers seem really small, but there are places where it could be really consequential, and it's really good to know, especially if you have a very tight tolerancing of something, if a displacement is going to start breaking things for you. That's why we would care about calculating these displacements. Let's take a look at one last example. So in this example, we're given a whole big setup of all these bars, and this load of 5 kips is applied, and we want to find out the displacement of points C, E, and B for these 0.35-inch diameter A36 steel rods, right? So a load is being applied, everything is being shifted, right? The rods are stretching, they're going through a displacement, and so we want to find out where those points end up because of this load. So let's talk about what's kind of actually going on in this. What's happening at each of those points? If I kind of break this down, so originally we have at the top here, this is rod, let's call it CED, this straight rod here, this 10-foot rod. And I'm going to free body diagram it up a little bit. So we have, if we look at this rod, we have this force from C that's holding it up, taking it up to the ceiling at F. So there's a force through C. There's a force through rod EB. And then there's that connection point at D. So I'll call that dx and dy. There are those reactions there. And we notice that we have this pin here that's allowing rotation. So the rods EB and FC are stretching, but it's pinned at point D. So what's happening is that because the stretching is being allowed, there's this sort of, not this dramatic, of course, but there's this sort of rotation that's occurring because of the displacement in rods FC and rods EB. So we get a displacement here. This is the displacement of point C, right? Point C would be moving down from this point down to this point. And then there's the displacement of point E. So it's much smaller. This would be the displacement of E, where we have the displacement of C. A note over here. The displacement of C is caused by the fact that rod FC is stretching, right? So this is due to the elongation in FC, in that rod FC. Whereas this displacement here from E isn't actually coming because of the stretching in the rod. It's coming because of this rotation of rod CDE, right? So as the elongation occurs at point C, that's causing the whole rod CED to rotate. So this DE, displacement in E, is actually due to rotation in CDE, not because anything is elongating. So there we'll probably use some ratio triangles once we have the displacement of C in order to find that displacement of E. Let's look at the rest of this, right? The bottom portion, where we have rod AB here. And rod AB experiencing the equal and opposite reaction of FBE. It experiences the 5 kips. And it experiences reactions at A. When AY and AX reactions because it's pinned there at A. So what I have is another set of displacements, right? This 5 kips is kind of pulling down that load. If I draw this triangle, it's being pulled down, where this is the displacement of point B. But we'll notice the displacement of point B isn't just due to this rod rotating. It's also due to the fact that this FBE is getting longer. So it's due to the fact that there's a rotation and because FBE is getting longer. And because of this rotation in this top one as well. Right? So this top, so FD, or FB, sorry, displacement of B is due to the rotation in CDE. So it's due to the fact that E moves and the fact that there is elongation in BE, sorry, in not FBE, just in rod BE, because rod BE is getting longer and because E moved, both of those things are causing B to move. So those are kind of our like rough free body diagram setups, just our ideas of how these things are moving. And so to go through and actually solve this, we're going to need the forces in those rods to find the elongation with our axial load equation. Our axial load equation again, that delta is normal times the length over area times modulus of elasticity. So we're going to need to find the normal forces through these rods that cause the elongation. And to do that, we kind of have these free body diagrams here because we're going to have to use statics. So I'm going to go ahead and look at my bottom rod here. So if I look at rod AB and use statics to solve for the forces here, I'm just going to take a moment about A, because I really don't care about the reactions at A. Really what I want is FBE to get the force through that rod and FC to get the force through that rod, since both of those are what's causing elongation. So if I take a moment about A, I'm going to have negative 5 kips times its distance from A is 6, plus FBE times its distance away is 12. So FBE is going to be, what is that, 2.5? 0.5 kips. Perfect. And so I can take this 2.5 kips and go ahead and do my free body for use the free body I have up here for CDE. And now I'm going to take a moment about point D because I don't care about it. I don't care about what these reactions are. I really just want to find FC. So since that's my only other unknown in here, we're going to have, scroll down just a little bit, take a moment about point D for just that rod, right? These are two separate individual statics equations that I'm doing, two completely separate systems or sections that I've broken out of the system. Moment about D, I'm going to get my FBE is 2.5 times, it's 2 feet from D, minus FC, which is 10 feet away, which gives me FC is 0.5 kips. Okay, right, so easy enough to apply our statics equilibrium equations to find what the forces are in those rods. Again, I'm not going to bother to solve for the reactions at A and D. I really don't need to, or really don't care. I just need those normal forces so I can calculate my axial load equation up here. So that's what I'm going to go ahead and do. I'm going to start with the simplest one that we've broken down up here. The delta C, right? Elongation from point C. So my delta C is going to be NL over AE. Let's break down what each of those are. My normal force is the axial force through that rod, so that's the 0.5 kips. My length is the length of the rod. I believe the problem statement gave us the length of rod FC is 2 feet. Now I'll need my area. I believe it gave us a diameter, 0.35 inch diameter. So that'll be pi over 4 times 0.35 inches squared. And then I need modulus of elasticity, which of course they don't give us. I have to go back to my tables for A36 steel, and this is in US units. So that's SI units. Here's my customary unit scale. I've got, what did I need? A36, that's right. A36 is 29 times 10 to the third KSI. So that's 29,000 KSI. Now again, notice all of my units are in inches except for this top guy in feet, so make sure we make that conversion, right? 12 inches in a foot. So now I've got kips, inches, inches squared, KSI. Everything is in the in uniform units, right? No mixing of units here. That I can get delta C when I punch that into my calculator is 0.0043 inches. Moves down by 0.0043 inches. Now again, since I have that one, I don't actually need to do an axial load equation for DE. I can just use this triangle relationship because DE is only caused by the rotation of this displacement here. So if we draw that triangle again, where this is DC and this is DE, delta E, I have my length of, 2 feet? This is 2 feet, and an overall length of 10 feet. So I get delta E over 2 equals delta C over 10. So my delta C is at 0.0043 inches. I get delta E equals 0.00086 inches. Just from the ratio of triangles there. So I think we just have one more, right? We needed to find the displacement of point B. So this is the one that's slightly more complicated, right? Because it comes from both DE and the elongation in FBE. So I'm going to need to calculate using the axial load formula, the elongation in FBE, and then just add on the delta E. And so my last guy here, delta B, is going to be delta E plus the elongation of B with respect to E. So this B with respect to E is our normal times length over area times modulus of elasticity. And we found already FBE is that 2.5 kips. 2.5 kips times the length of BE. Our problem gave us as 1.5 feet. And again, I'm going to go ahead and do a unit conversion here, 12 inches in a foot. And then I'll just need that area and modulus of elasticity. Luckily, that's the same as before. I over 4 times 0.35 inches squared times 29,000 KSI gives me a delta of D or B with respect to E is 0.0161 inches. I'm just going to add these two guys together. My DE was 0.00086 plus 0.0161. So my actual delta B is 0.017 inches. And that's it. That's all three displacements that they asked for. Again, just combining using these axial loads, using your statics, using relationships with each other. The most important thing in this one is understanding where the elongations are coming from, how the displacement is occurring. Is it coming from rotation or is it coming from elongation or both? That's the thing that can be really easy to trip you up. If you can understand kind of how things are moving, you can find these displacements with the pretty simple equation.